today. This has a lot to do with what we'll be doing in class, believe it or not. A train sounds its horn while it speeds toward and then passes you. What do you notice, if anything, that might be unusual about the sound of that horn?
It gets quiet as soon as it passes.
Okay, so it might get a little bit quieter. Stretches out a little bit. Michael?
I feel like it kind of like distorts, kind of like once it kind of like stretches out. Like when it's coming towards you, it's more compressed.
Okay, so that's kind of getting more towards the reasoning there. Yeah, you're headed in the right direction. But overall, what do we hear that's sort of strange? Keegan?
I think when it gets closer, it's like a way different sound when it's farther away.
It is. Any guesses on how that sound changes? What's different about it, aside from volume? Frequency. Absolutely. So, I'm going to play a sound for you. This is a fire engine approaching. And eventually you'll hear a change in that sound. And when you hear that change is when that fire truck has passed you by. So, my speaker turned off.
I don't think it's going well. I'll just sleep the whole time.
All right, so listen up. Here is the noise. Right now it's approaching. Whoa! What changed? It changed pitch. The frequency changed. Let's listen again. So absolutely, the pitch changed. And what changed about the pitch? Did it get higher or lower after it passed? It got lower, yeah. So to answer the question, you can just say that high pitch as it was approaching, low pitch after it passed. High pitch as it was approaching, low pitch after it passed. So I've got a special, we call that effect the Doppler effect. And I've got a special little Doppler ball right here. And it's going to annoy you, but that's okay, because it's for science. So I'm first going to kind of throw it past everybody, and then I'll throw it back this way, probably end up hitting the camera or something, and then we'll play catch for a little bit. And hopefully you can hear kind of the same effect. Could you hear that?
Yeah, kind of.
And coming back. And hopefully you can hear it change pitch there. And now let's play catch. Oh, yeah.
Bro,
What else want to say?
not the girl.
Holy
Wow.
That came out! The thing came out! It's on the ground.
Where'd it go?
Oh, man. Andrew,
Gosh, you broke it!
Well,
Let's do it with my lefty, alright?
that went according to plan.
Twice.
So that's a Doppler ball. It was the Doppler ball. And it's super cheap. I just got to stick it back in there. This probably cost like $40. Things out of science magazines are so pricey. But you have a higher pitch when the object is approaching. After it goes past you, it has a lower pitch. And so we need to figure out exactly why that's occurring. And we can do that using that same little ripple tank applet that we've used in the past. So check this out. Would anybody anybody like to try and explain what's happening before this comes up? Okay. A decisive class. That's good. So this is our object. We're going to say this is our sound source, and it's going to start moving down. And the waves that you see, you can think of as just sound waves moving out in every direction. Let's see what happens when the object starts going. Do you see what's occurring here? What's happening? Should we do 3D?
Yes. Whoa! Oh yeah!
Dude, it's like popping right out at me.
No, I'm talking to you, your uncle. Yeah. What the heck?
We're doing it at the end of class. You gotta pay attention.
So what's happening with the waves here? They're less defined, you said? Right, so it has something to do with the way the waves are spreading. That's absolutely true. Who wants to take this to the end? We're rounding second here.
I think the sheriff said it pretty well.
Yeah, they're sheriff.
Yes,
Wait,
Michael.
the sheriff. Are you the sheriff?
I think it's
Sheriff.
I think more sound waves
Wait, can I see
like closer.
Keep it down a little bit, guys.
Because as it moves along, it's moving with some of the sound waves, so it'll put more sound waves together.
Yeah, so when we're talking about how this thing is moving and how the sound waves are affected as it moves, we have to realize that if we're listening in front, we've got waves that are much closer together. And if you've got wavelengths that are compressed, you're going to hear a higher pitch, a higher frequency. If you're behind it after it passes you by, you've got elongated wavelengths. And those elongated wavelengths are going to give you a lower pitch. And that matches up with our observations. That's called the Doppler effect. And that's what we see here. Before we dive deeper into this, I want to just mention the Doppler effect is also true for light waves. The light waves that we've dealt with, like the red light, those are really long wavelengths. Purple wavelengths are much shorter. So in the same way that when an object making noise is approaching you, the sound waves get compressed, light waves do the same thing if you're going towards a light source. So, technically, if you're driving along and you see a red light and you blow right through it and get pulled over, you could tell the police officer that you were just going so fast that those light waves got compressed enough that it looked like a green light to you. Now, you'd have to be going at roughly half the speed of light, so it'd be interesting to see the response. But that would technically happen.
Well,
Yes.
What if you just told him like you just didn't have your eyes open?
I'm sure that would go over very well.
Oh crap!
That's one of my favorite. I love doing. That's one of my favorite pranks to do on my wife. Like I'll be driving, she'll be in the passenger seat, and I'll just pretend I'm asleep, just like closing my right eye.
Oh my god!
She freaks out. It's great.
No, you know what I actually no joke do?
Yeah.
When like my parents, I had to like they would like take me driving before I got my license. I
Uh-huh.
would take my hands off the wheel and go like this. And I'm like, it looks like you're. It feels like you're running, and they'd be like, put your hand on the wheel.
That's awesome.
That's how I got that website. You so virtual. Where'd you find it?
Hey.
I typed in like ripple tank because I used to actually try and do that with actual water, and it got way too difficult and time consuming. So I was able to just do it on the board. If you type in like ripple tank, it's one of the first things that pops up. Okay, so we're going to be talking about the Doppler effect, and we're going to be able to figure out exactly how these frequencies are changing based on how quick these objects are moving.
How did you stop about chicken nuggets?
I love chicken nuggets.
If you don't like chicken nuggets, you don't have a soul.
Wow. I suppose it is Halloween, so it's kind of dark. If you have your formula sheet with you, take that out right now, too. But you will be taking just a few short notes. Very short notes.
Like, your definition of short, my definition of short,
That's possible. Hey, Ethan.
Where was you?
he was sleeping.
No one goes down
This is
to
why we
the-
sent the pictures.
Now, you do not need to take these notes if you have the reference sheet that tells you what all the letters mean on the formula sheet. If you've got that, you don't have to copy this down. If you want to just copy it down to have it handy, feel free. But the main thing is, on our formula sheet, we're mostly going to be looking at all those equations in the giant sound box in the top right. So we want to make sure we know what all those letters stand for before we do that. So F stands for the frequency emitted by the source. The frequency emitted by the source is this. It's what you hear when everything is just standing still. This F, with a little apostrophe, is the observed frequency. So this is the frequency that you hear as it's moving. It'll be a higher pitch if it's moving towards you, a lower pitch if it's moving past you. Vs is the speed of sound. And again, these are just the letters that are in that big equation box for sound. Regular V is the velocity of the sound source. And V with the apostrophe is the velocity of the observer. So in the example that we were doing in class with us sitting here and listening to the fire engine, we were holding still. We did not have a velocity. But there are scenarios where both the sound source and the observer are moving. We got to make sure we know what to do with those. For instance, my dad, when he was a kid, tells me stories that he and his friend George would jump on moving trains and ride them for a while and then get off. So, yeah. I suppose times were different in the 60s. But yeah, they wouldn't do it for trains that were moving really, really fast. But yeah, they would do that, just hang on for about a mile and then walk back home. Yeah, yeah. It'd be kind of interesting to see where you end up if you just hop on a train and then get off at the next stop. Wonder where. There you go.
Run away from mom and pop.
Any questions on what these all mean? Okay, that means we're in good shape, and I'm going to erase them. Yes.
You know it's my dad's birthday today.
I did not know that.
Yeah, you can wish him a happy birthday.
Absolutely. Sounds good, for sure.
Big year, 26.
Nice.
Big year.
46? I was going to say, he looks...
46?
Only 30 years older than me.
He looks like he's 20.
What?
He had you when he was 4.
Yeah, I joked earlier that it was his 20th
All right. So this is your formula sheet, and these are the rest of the notes. These are all the equations you need to do in order to solve Doppler effect problems. So we'll talk about this later. We're going to make sense of all this right now, though. So if you have a stationary observer and the sound source is moving, or maybe you're moving and the sound source is holding still, this is how you would solve for different values. This is how you'd use this equation in order to solve for the velocity of the object that's moving. You would use this equation to solve for the frequency that you would observe, because obviously this frequency that it's producing is different from the frequency you're going to hear if it's moving towards you or moving away from you. This is the equation you would use in order to solve that. And we just wrote down what all those letters mean. If the object is going away from you, then you use the ones where it says leaving. So up here, when you've got at least one thing holding still, you can solve for both a velocity and a frequency. But if we take this one step further, and we get to a point where both the observer and the sound source is moving, where we're moving and whatever is producing the sound is moving, things get a little bit more complicated, but not really. Because we know what all these letters mean, we just have to make sure we're clear on what each of these scenarios are. So there's 4 possibilities. Take the 2 cars from my childhood. They both glow in the dark, and they're both awesome. We're going to use them to figure out which of these 4 scenarios each of these are. So here's scenario number 1. So which of these 4 do you think that corresponds to? Same direction leaving. Because they're going the same way, but they're getting further apart. What about this? Yep, opposite direction, and they're approaching each other. What about this?
Opposite direction leaving.
Opposite direction leaving, very good. And, of course, last but not least, same direction approaching, because they're getting closer and they're moving the same way. That's really all there is to this stuff. No, that's not too bad at all. There is one extra thing I need to add to this, though. I give you the homework, which will be due on Tuesday. And I'm going to warm it up. So basically what we've got here, and I can't, because I'm recording this, I can't show the video, otherwise it might get blocked and flagged by YouTube. So what you've got here is you've got 2 different tuning forks. And they are of different frequencies. That's all you need to know about this. And at the end of the video, he hits them both at the same time. And you can see what happens. They're both very close to the same frequency, but not quite the exact same frequency.
Can you stop recording and then let us
I'll have you watch it after I finish the recording, I think. So here we go. You hear that waviness? Is that what? No, it's something called beat frequency. And that's what we have to talk about next here. So I'm just going to go back to the PowerPoint with our formulas. And thankfully enough, beat frequency is on your formula sheet. So you don't need to take notes on that either. But basically what happens with beat frequency is this. If you have 2 tuning forks, and say one is 500 hertz, and one is 499 hertz, your beat frequency is just going to be the difference between those 2 numbers. So if they're different by 1, your beat frequency is going to be 1. If one is 500 and the other is 490, then your beat frequency is going to be 10 hertz. And what this means in terms of those waves that you heard, you would hear, if it's 1 hertz difference, you would hear as a frequency, as a beat frequency, 1 hertz, and that corresponds to 1 beat every second.
What's TB?
This is beat period. If you have your beat frequency, you just take the inverse, and that's your beat frequency. Very, very similar to our relationship between period and frequency down here. So, questions on that. And it is absolute value. So if you put 95 here and 100 here, you're not going to have a -5 frequency. You just take the absolute value of that number. Where this gets a little tricky, and I want to make sure that we're clear on this, let's say I know that one tuning fork is 100 hertz. And I'm hearing a beat frequency of 20 hertz. So frequency 1, 100 hertz, that's one of the tuning forks, but I'm hearing a beat frequency of 20 hertz. What is the frequency of the second tuning fork then? 80 hertz.
Could it be 120 too?
Absolutely, and that was the point I wanted to make with this. Because all the beat frequency does is tell us the difference between the two. We don't know if that second tuning fork is 80 hertz or 120 hertz. You need to be aware of that.
Should we just write both down?
Yeah. I mean, it could say that, if it says you're moving towards an object, you would know it's the higher of the two, if that's something. But yeah, that'll come into play. So make sure you're aware of that. The last thing I want to mention before I hand this out is this. There's one question where it gives you a speed in miles per hour. In order to convert this to meters per second, what you need to do is multiply by 0.447. That's something that you need to do. There's one last thing that I'll mention once I get these handed out. Good news about this piece of homework is twofold. Number one, it's not due till Tuesday. And number two, it is Ninja Turtle themed.
And number 3, can you do the last thing for us?
Yes. On the very top, in big bold letters, it says, for the problems where the speed of sound in air is needed, use 343 meters per second. That is important because you're going to need that number in order to figure out a frequency or a wavelength or something on this homework. Because remember, this equation holds true as well. For the questions on the homework where you need to use this, your wave speed is 343 meters per second. That's the speed that you need to use for the speed of sound when it's applicable. Here and here and here and here and here and here and here. So Vs, that speed of sound, is listed as 343. Don't forget about that. And this equation comes in handy, especially on number 2. You're going to need this for problem number 2. Alrighty, I think that should do it. Yes.